Y'all see this? What I'm looking at is this is the basically the actual look on the controller itself, 1200. Just about every PLC I've seen has this one. This one is a little different. And it seems to think you already know a lot. But what I'm looking at is right here where it talks about installation. And most of the stuff we've already done, but this tells us, you know, the dimensions of the thing. It tells us power budget. It tells us, you know, mounting of the thing. It tells us how to install signal boards. Y'all know for the 1200, y'all know what the signal board is, right? Or module. This is a little optional module that you can upgrade your PLC without the little one on the center. Yeah, they call that a signal module, or right here that plugs in right here, and that's where we put the analog output module in. So basically, you can do basic upgrades to your PLC without mounting it on a DIN rail or without, you know, buying a big module for doing a little thing. Does that make sense? So what we did is we only added one analog output. That's what our signal module did. And there's all types of signal modules that we could add. Signal module, yeah. And that's the one they call that plugs into the center. So let me go back where we installed it. So this is adding this shows us the procedure for, this shows us the actual procedure for adding a true module right on the side. We looked at that, y'all did that. This shows us how to add what they call a signal module, right? So you snapped it out and you just snapped it in here, which was just a basic small upgrade to the PLC. So we added, the PLC itself comes with two analog inputs and then no analog outputs. So we added an analog output just by snapping in a signal module, right? Pretty easy. This shows how to add the module onto a DIN rail, and then we did that and then slide the connector, the snap in there, right? And then communication modules go on the left, and then IO modules go on the right. This shows us how to snap out the terminal. So what's nice about this PLC is that literally you can put a screwdriver, and there's little notches in it if you look real good, and then you can do what? You can pull it forward and that'll snap out the actual terminal board. Now, why would that be a nice feature? It'd be easier to connect if it was off the PLC, but the primary purpose is for us to do real fast maintenance. So what happens if we got a PLC that goes bad? Well, instead of me going up there and having to rewire the whole thing, I can just take the PLC that's out there, pop its terminals out right, bring in a new one, put it in there, pop them in, upload the programs. Hopefully you keep backups of your programs, right? Upload the new program and you're what? You're ready to go in a matter of basically minutes, right? Or you could even do this, you know, upload the programs before you even did what? Put it on the line. So now you can carry one PLC or maybe a couple of PLCs that you just keep for what? For spares, and then you can get it fixed with it. Also, installed, and then it shows us how to install the terminal boards. So if you ever looked at the 1500s that's on Siemens, those are hardwired. So if we had to replace that thing, we would be messed up, right? You understand? Unless they do it the way Festo does it, is they install cables, and then they plug the cables into the terminal board. And in that way, if you needed to change the PLC, you just have the cables on there, and you come back and cable it up real fast, which is also basically what they did on the Amatrol line. Also, it shows us how to expansion cable. Now, what that is we have the ability to expand it even into another PLC, right? Connecting teleservices, and then where I wanted to get to, SIM cards, so we can increase the memory. We could put the program in a SIM card, right? You understand? That makes sense. Everybody knows what SIM stands for. Yes, you have SIM cards. Yeah, I'm not really sure. I need to go back and check that out, because we would do it because we're living in a because there's always a need to be able to pass information from one PLC to the next PLC. Now, if I've got a PLC running a single thing, then that's no big deal. If I have multiple PLCs that's in a system, then there is a need to be able to have the PLCs communicate with each other. Or, for example, not even PLCs, even HMI panels. So, what would be more beneficial, to put an HMI panel on one PLC, or to use one HMI panel that you can do whatever you want to on any PLC on the network? So connecting PLCs together, even robots together, so they can transfer information, let this robot know what happened over here, what this computer knows what happened over there. It's basically the same need as I have right here, right? You understand? So my computer is connected to a network. So what can I do? We communicate with other things. We can share things. We can set up what we call libraries, which hopefully we can get into that. A library would be something in one PLC that any PLC on the network can access. So if I update something in my library and then the other PLC accesses that library, then we're dynamically transferring information between one PLC to the next. So instead of every PLC trying to sense a part when it gets to it, the first PLC can sense the part and then just do what? Tell the other PLCs, okay, this is the part we're putting together, right? Does that make sense? Instead of like on the Festo line, so the Festo line, we deal with three different colors. And the problem is that information is not available to the next PLC. So what does that mean? Well, every module that needs to know the color has to resense the color instead of doing it once, which would make it more efficient. This right here, I'm not really sure. I'd have to go back. Usually we do that through a standard interface, like, you know, like Profibus or Profinet or DeviceNet or something like that. So I'd have to go back and research that. That's a really good question, as far as what would be on this side over here. This looks like it's just a terminal blocks. So what this is on the On the right side, I don't know. I need to look at that. Because SM would be signal module. So anybody find out what SIM stands for? I wouldn't come. It's not memory. This is memory. Memory? Yeah. Subscriber identity. The way I learned it was single inline module. Because if you ever look at one, all the pins are what? They're in line, right? Single inline memory card. In computers, we used to call them SIMs because we call them single inline memory modules, but this would be a single inline memory card. So if you ever look, it's got pins that are always in line with each other. Now it might be two-sided or it might be one-sided. Then they came out with DIMMs, which were dual. This is what, yeah, originally when they put the memory modules in the computer, so we went from individual integrated circuits. You should have seen the memory when the computer first came out. It was huge. Then they came out with a method where we could upgrade the memory in the computer really easy. So they put them on the memory modules. And the first memory module that they came out with was called a SIM, which was a single inline memory module. So the way the memory, I'd have to go find them. Y'all probably seen them before. But it appeared that it had two lines of pins, and they wasn't really pins; they were actually connectors. But normally in electronics, any electrical connection you make to a component, we call it through a pin. So we would call this right here a lead, or on a memory module we would call these things pins, or on an integrated circuit. So what they did when they first came out, dang it. So these were SIMs. You ever seen those before? Each one of these was memory.
We had messed with those. There was some I did in digital. One thing like that,
Don't know. I don't remember. Well, what they were doing is this was a key. So when they came out with different variations on it, they would move this little notch around. So that means when they came out with new memory for the computer, these had these little tabs on both sides, but they were parallel with each other. So that way, the computer had two chances of making a connection with any side. These things clamped into a C. So you'd come up here and you'd put them in and you'd bend them down and then they would snap in, which is basically, if you opened up these guys, these would be basically the same module, but they're a little smaller. After that, so the S single inline memory, then they came out with dual inline memory. And we call these DIMMs. And this is what your computers, your big computers, your desktops run now. They look almost identical, but what they did is they Now the two sides are independent of each other. These insert straight down, where the SIMs, you'd put them in and you'd lock them down. So if you looked at the memory in this computer right here, it would be a dual inline memory module, but it snaps down similar because you don't want it to occupy a lot of vertical space. So this is memory. So this is the DIMMs. This is the way they plugged in. So you come in and put pressure on both sides, and then it snaps. When you push them down, they would come up and snap in. Which is really nice now, because now you could upgrade the memory of your computer, as long as you bought the right module, because it still had the key in there. So if you could look in the slot right here, you'd see that it's got a mail key here, and then it had a little slot cut in the memory module. When they changed the way they operated, the electrical characteristics, all they did was just do move the key. So if you ever went out and upgraded a memory for your machine, you need to make sure. So DIMMs now we're in, I think, built-in memory module. I think we're in version 4 of these guys. Huh? I think it might be 3. We might still be 3. No, DDR was a real neat feature that they decided to do. So double data rate means basically you use these things in groups of 2. So you have another module and they'd be side by side. What would happen is the way your computer gets DDR means double data rate or full channel, you would access one byte of memory over here, and then the other byte of memory would be the other module next to it. If that makes any sense. And that doubled the data rate that you could send it. So when you access memory, memory has what we call an access time, which is how fast it can give you data. So what was happening is you was hitting the same memory bank over and over and over again, and you had to wait on this guy to get through before you could access the next one. Does that make sense? So when they went to dual channel, they would access this guy, and then they'd leave it alone. Then they'd come over and do what? Access the next one. So they went all the odd even addresses were in one module, and all the odd addresses were in the other, and that increased the speed quite a bit. Unless you only put one memory module in. If you put one memory module in, then your computer ran a lot slower. Now, how did we get off on that? SIMs. So probably in a cell phone, that would probably be true what the SIM stands for, because that SIM card contains what? All the identifiers about your phone. In computers, it's not. So I imagine this is just extra memory. This has nothing to do. This would be just a memory module where you can either, also SIMs are non-volatile memory. What's non-volatile? Doesn't lose its contents or remove it. But this is. Yeah, I'd imagine that's what you can do. We've never had the opportunity to do that, so I'm just thinking what it could be, or either that to increase the memory, or put what we have in the PLC, most PLC, and we saw this over there in Intro. We came over there, and somebody had come up there and turned our PLCs off, and then right off the bat, a lot of y'all got a fault right off the bat. Now why? Because it lost its program, because the memory, the main memory in the computer, to make it faster, is a volatile. So what they do is, if we went over there into all these PLCs, we would see a battery in there. And if that battery goes dead, then you lose the memory in the PLC. So it was telling us, they gave us a fault, which is there was no the PLC was basically totally empty. So we created a dummy program, and we uploaded into it. And once it got something in its RAM, it knew everything was okay. So, but we've had such good increases in the speed of non-volatile memories with the flash drives and USB and the speed of transfer now that we have, that most I don't know. I don't even think the 1200's got a battery that I know of. We'll look and see. Yeah, well, that would be what the memory that we use doesn't draw much. Doesn't draw. Well, that's not true. I don't even get into that. This is what I wanted. A lot of people don't understand the way these guys right here work. I don't think we did this. We should talk about this in advance. So what we want to do is we want to. So this is this is a symbol for something we call an inductor. Did we talk a little bit about that? So we have two devices that we use as filters. So filter is something that gets rid of things that you don't want, right? Filters it out. So like your coffee filter that you put when you make coffee. If y'all make coffee every morning, it filters out the grains, right? So we have two devices that we use as filters. And we also use them to time. So if you take AC, or when y'all take AC, if you're in the AUT, AC is an elective. If you're in the ILT, AC is one of your core classes. And what's the difference between AC and DC? I was laughing when you said go both ways because I've heard that term used a few times, which has nothing to do with PLC. So AC constantly changes directions. DC doesn't change direction. So it always flows in the same direction from a negative to positive for what we call originally when it still only flows in, no. Well, it don't make any difference. It still flows from negative to positive. It's just that if we put on L1, L2, if we put the minus on the L2 and then the positive on the L1, then it's going to flow from left to right. Okay. If we put the negative on L1 and we put the positive on L2, then it's going to flow from right to left, but it's still flowing from negative to positive. The problem we had was this is before they realized what was flowing, and they say, okay, everything usually flows from the high potential to the low. It's like wind rotates or blows basically from what? High pressure to low pressure. So when they first realized something was flowing, they said, okay, we're going to name these things positive and negative. So it was just named that, right? You understand that? And they came up with a symbol. Originally, they thought it flowed from what? Positive and negative. That's what they thought. Before it was finally proven that what was actually flowing was the electrons in the device was actually moving. So unfortunately, when they were developing when they started developing these electronic devices, they drew them up as current was flowing what? Positive, not one direction, as current was flowing positive to negative. So when we look at a symbol for like a diode, when we look at a symbol for a diode, it's going to be drawn as an arrow.
The line with the little arrow pointing down, right?
So this is a symbol of a diode. So we come in, put this guy arrowhead. This is supposed to be filled in, but a lot of people don't, because if you don't fill it in, and then we put this. Now, which way would you think current flowed? Huh? Well, this is the way current flows, so current actually flows against the arrow. But when the symbol was developed, they thought what? Positive. They were thinking positive flow, positive to negative. So this guy current flows against the arrow. So to make this thing work, so let's come over here and we'll just put a DC power supply. And we'll put a resistor, of course. Let's say 12 ohms. And this is DC. Then what we look is this is, if we follow this around, then that's pointing toward the negative. A lot of people says the cathode has to be negative and the anode has to be positive, but that's false. It's just got to be pointing toward the negative, right? And this out here is pointing toward the positive. Now this guy here is acting like an open switch. So what does that mean? So if I measure across my resistor, what's it going to measure? Huh? Yeah, it's going to measure 0 volts because there's no current flow through it. If I measure across my diode, it's going to measure 12 volts because it's acting like an open switch. That makes sense? Okay. Now, if I come up here and change the polarities, oh, I could have left my. So what we're going to do is we're just going to change the polarity. So I'm going to come over here and make this one long and make this short, right? You understand? So on the symbol of a DC voltage source, originally this was a symbol for a battery, but now it's a symbol for any DC voltage source. Right? You understand that? So we can come up here now. Now this is positive. This points toward the positive. This points toward the negative. And this guy here, we say it's forward biased. And now current's going to flow. So here, when it's forward biased, it acts like a what? Closed switch. Acts like it is not. So now this goes negative, this goes positive. Now current can flow. Now it depends on what type of diode it is. The predominant diode is made out of silicon. We have two types. We have germanium, which you don't see hardly anymore. Now, we say it acts like a closed switch. It is not a closed switch. It's a semiconductor. Semiconductors always drop a voltage. So silicon drops around 0.7 of a volt or 700 millivolts, and most people don't use correct engineering notation there. So that means if I measured this now, this would measure about 11.3 volts, and this guy here would measure what? About 17. So we have transistors. This is what we call a non-pointing in. To make this work, we have to make the cathode negative in respect to the base. So the cathode does not have to be negative. It's just got to be negative in respect to the base, right? You understand? For example, I'm going to do this on purpose. I'm going to put a resistor right there. Okay. And we have to have at least what to turn it on. Guess what? About 0.7 of a volt to turn it on. If you get below that, it cuts off. If you put it above that, it turns on. And so if I came over here and put plus 5 volts over there, is that above 0.7? Okay, so how much voltage would I have across this resistor right here? 4.3, because it's a series circuit, and we drop that 0.7 anytime we have a P-in junction. That's what it is. So to forward bias a N P-in, we have to make the base positive in respect to the what? So this would be plus 4.3, and that's 5 volts. So the base don't have to be positive. The base has got to be more positive than the emitter. And that's true for diodes too. And some people say, I could put that on a test. I said the base has to be positive and the emitter's got to be negative, and somebody would say true and they would miss it. It's just that the base has to be more positive than the what? The emitter by 7/10. And 7/10 is an approximation. It varies with temperature, so that's what we call an approximation. Silicon is about 0.7, germanium is about 0.3. Silicon is more temperature stable. It don't want to change with temperature. Now the problem is that if I come over here and put a minus and a plus, this thing would be reverse biased, right? You understand? Everybody okay? But if this plus keeps going up, sooner or later that sucker's gonna break over. And if it breaks over, it's gone just like that. So when we look at these diodes, one thing, or any p-n junction, there's a rating on here called the breakover voltage. And this is how much it can block. Because sooner or later, this is not an open switch. There is a path through there, right? You understand? So what happens is we force current through a lot of voltage and it burns up just like that. So if you ever see the breakover voltage of a p-n junction, it would be what? It's going just like that. Now, transistors are rated kind of different, like V sub CEO. So if you ever look at a transistor, so this is voltage collector to emitter. So this is what? We've already talked about. This is the collector. And this is the emitter. And this is the base. So what this means, voltage collector to emitter with the base open. So the transistor's cut off. If you ever exceed this rating, then the transistor could be damaged. Because what you did is you just forced current through a reverse bias junction, right? Does that make sense? So we've got these outputs of these sensors. We got these outputs of these PLCs. And now we know that when we output sourcing, so if our PLC is sourcing, this is probably the way the output's going to be. And then we'll hook up our load right there. And then this up here might be plus 24 volts right there. I need to get rid of that other transistor down there. And these are the 1200s. So the 1200s are sourcing outputs. So what that means, if it's DC, we're outputting on a transistor. If something happens on this load right here, or something happens to the 24 volts and I see the breakover, that's not our problem. The problem is this load. Because if it's a relay load, that means we got this right here. We got a bunch of turns of wire. Everybody understand that? And if it's DC, then what happens when we put current flow through a conductor, it creates a magnetic field. Magnetic field. Everybody follow me so far? Creates that magnetic field, then it's going to either pull in a armature or a plunger that's going to move, and the contacts are connected to the plunger, and it causes things to make or break. Everybody follow this so far? Now the problem is that those coils of wire store a charge. So inductors and capacitors store DC. Capacitors do it by electrostatic field, Inductors store a charge through a magnetic field. So if we're going to use an inductor, a DC coil, then if I put 24 volts and it's nothing but coils of wire, right? You understand? Now, what determines the resistance of a coil of wire? I mean, what determines the resistance of a wire? Good, good. It determines the resistance of a coil of wire. Okay, good. So somebody said material. That's one of them. M-E-T-E-R. Material. What's next? That's not material. I'll spell it. Go ahead. Well, it is ohms. So there's no such thing as 0 ohms. Everybody understand that? There's always some type of resistance there. So even your metals, even your conductors have resistance. They're rated in ohms per 1,000 feet, right? You understand that? So what determines the ohms per 1,000 feet? The material it's made out of. So aluminum would have a higher ohms per 1,000 feet than copper. Copper would have what else? Besides, Yeah, but that's material. So material, we've got one of them. That's material. The material it's made of is one factor that determines the ohms per 1,000 feet. What else? The size of the conductor, the bigger it is, the less ohms it has per 1,000 feet. The smaller it is, the more ohms it has per 1,000 feet. What else? I said per 1,000 feet. Now the length determines how much ohms a resistor has. And then what's for? My computer's lagging behind me a little bit. The temperature that we're operating the metal. Of the metal. And metals, the hotter they are, the more resistance they have. The cooler they are, the less resistance they have. That's why when they have superconductors, they super cool them. They freeze them, right? You understand that. But bring them down as cold as they can possibly get them, because one of the main things, we use this feature, temperature, we have what we call RDTs, resistive temperature devices, which is nothing but this. A bunch of coils of wire, and we measure the change in resistance with what? Temperature, very limited. Okay. So the material, the size, the length, and the temperature. So what that means, if I'm going to put DC across this coil, I'm going to have, the only resistance it's going to have is the material it's made out of, the size it's made out of, and the length. We're putting DC on this, guys. So that means these DC coils are going to have a lot of turns of what? Of fine gauge wire. A lot of turns of fine gauge wire. Now AC gets what we call X of C, X of L, which is equal to 1 over 2 pi FL. So an AC coil varies its opposition with frequency. So that means if you ever look at an AC coil, it's going to have fewer turns, because not only does it have R, it has something called what? X of L. If you ever take an AC coil and put it across the equivalent DC, you're going to create a fire, because you have very low resistance, right? You understand that? Now the problem we have is that if I put DC on that coil, that sucker is going to build up a charge. It's going to charge. Now the problem we have is, how do we electromagnetically create an EMF with magnetics? What do we need to create an EMF with magnets? Let's go First of all, I said with magnets, so let's go down the list. So we gotta have a what? Yeah, we gotta have a magnetic field. Okay, what's the next thing we gotta have? Let's go. With what? Gotta have a magnetic field. Next thing we gotta have is we gotta have a what? Conductor. Then what we gotta have? Relative motion. You understand why I said you can't have relative motion with a magnet with a magnet. And y'all know what relative motion means. What does it mean? Yeah, the motion between the two, right? Okay. Yeah, that's the amount. Now, what determines the amount is what? The strength of the field and the number of loops that we put in our conductor. Conductor loops. Yes, thank you. Yeah, looks like so. And then 3 is the speed of the motion. Now the problem is, I come up here and I put DC on this coil. What does it create? It creates a magnetic field. Right? You understand? Right, okay. Alright. Now that magnetic field builds out around that coil. But what happens when I turn off the thing off? Well, that magnetic field comes collapsing down into the coil that it was expanded out of. Now what do we have now? We have a magnetic field. We have a bunch of conductor loops, and we have IC. This guy is going to generate a voltage that is opposite of the applied voltage, because when we applied voltage to it, it expanded out. Now what's it doing? It's collapsing back. Well, the problem is I might come up here and charge this thing up to 24 volts. Now it's got a magnetic field. I turn that 24 volts off. That magnetic field collapses back, induces a counter EMF, bops my transistor. It's like that. Unless I did what? Okay, so I'm going to come up here and pause this, and we're going to go. Now, the way the problem we have with AC, if I use a diode, one way would be short circuit and the other way wouldn't, right? Now, we could come up and do something like this, but there's really no need. But now what we're going to do is that if this gets up too big, it would cause one of them to go out, right? You understand? So originally they used a device called a diac. And a diac is really weird. If you look at the characteristic curve on a diac, it would conduct a little bit. And then when it got up to a certain voltage, it would break over. And then in the opposite direction, it would come over here. And when it got up to a certain voltage, it would break over. But it was designed to do that. It was designed to break over in the reverse bias direction. So for years, they used these things called diacs. But what they went to another type of thing was something called an MOV. So that's what you do now. You can buy these, and they're rated at a voltage, like 320 volts. So if you got an NOV rated at 320 volts, that means as long as you operated it below 320 volts, it wouldn't work. As soon as you got up above 320 volts, it would break down. But it's designed to do that, right? You understand? Sometimes it would hurt it, sometimes it wouldn't. If y'all have any surge suppressors on your, if you don't have surge suppressors on your computer and stuff at your house, you're living by the grace of God, but sooner or later lightning's going to get them, right? Surge suppressors. If you ever took them apart, right across the line, they got an MOV out there. And so what they're deliberately designed to do is to break over at a certain voltage, and surge suppressors will have a circuit breaker on. So when they break over, it creates basically a short circuit through your MOV and does what? Kicks the breaker. Sometimes it damages the MOV, sometimes it don't. So we use these metal oxide varistors. These are bidirectional. So this is what you should have across AC coils. So AC coil should have a what? An MOV, right? You understand. And then DC coils should have a diode. Are you okay? That makes sense? So we still need to suppress AC because you don't know, you're still charging up that coil and you don't know exactly when you're going to turn that AC off. And if you're doing it with a relay, the problem we have with relays is that they might arc. But a lot of your solid state devices use something called a triac. Triac. Which basically almost has the same symbol. Of course, this is no. Some people call these things solid state relays. MT1 and MT2. I can't remember. I think they call it a gate, I'm sure. So these are solid state relays. So if you've got an AC output and it don't say it's a, what advantage does a relay output have on a PLC? You can put AC on it, you can put DC on it, you can put all different types of voltage levels on it as long as you don't exceed its maximum rating, which is usually 200 or 300 volts, right? You understand? They don't care. What's the biggest disadvantage of relays? Yeah, the speed they operate. They operate at a fairly low speed. So if you need extremely fast switching rates on the output of your PLC, then you're not going to use relay outputs. If you want to control AC, then you're going to use it with a triac. A triac, you can bop those things if you exceed the breakover voltage too. So if you got a relay output, odds are running AC, there's a high probability you don't have to use any type of suppression circuits on relays. When you get into these solid state outputs, then you need to what? You need to make sure you put suppression because you can break those things over. That makes sense? So we're not going to have to worry about it here because all these suppression devices are already on our coils for us, right? You understand? But if you were out there, if you get the privilege of actually wiring up the whole PLC circuit, which some of y'all might get into that, then you're going to have to remember to put those suppression devices on these relay coils because those guys can really cause some suppression devices. And that's what they do. They suppress that counter EMF. So AC, we use what? MOVs. For DC, we use diodes. Okay? So that's what I wanted to show y'all. But all these things give you a good idea of what you need to do and what you need to do to suppress those, right? You understand that? Here they're using they're also putting a capacitor and a resistor up here. And this what they're doing is they're coming over here telling you what values you need to do what. So 230 volts AC, right? Then the resistor should be what? 270 ohms with a 5 watt rating, and your capacitor should be 1,000 nanofarads, which 1 microfarad, huh? What's that? Yeah, what they're recommending is also put a little RC time constant circuit in there, which we're not going to talk about. So, press AC, they're recommending you use the sure working voltage of metal oxide at least 20% greater than the nominal line voltage. Use pulse rated non-conductive resistors and capacitors recommended for pulse applications such as metal film, which is about all you can get now, guys. Metal film resistors. We used to have carbon resistors, but metal film is usually all we get now. And then what they're saying is that the MOV needs to be rated at least 20% higher than the voltage you're operating at, right? Understand that. The nominal voltage, right? I understand that. And then you need to use this chart. And this would be also in the Siemens PLCs, Allen Bradley, where they would have you what? Size the resistor. They don't talk about diodes. They're talking about a 4001. 4001 has a breakover voltage of not much. Seems like it's like 70 volts or so. On your diode, let me bring this up real quick. Y'all see this? So this is the 4000 series of diodes, which is what every one of these used here. And this is the breakover voltage. What you want to make sure, you want to choose something that's got a breakover voltage. Like 1,000 volts, right? So they're using a 4001, but if you were operating on 120 volts DC, you're not going to see that much. You might have to move to 4003, right? We're operating on 24 volts, so this is the one that we're using. This is another chart. You can find these charts. That was MOV. On diodes, so they're saying your it don't mean you can't have more. It said at least 20%, right? And why they say at least, because you might not be able to find an MOV that's rated at exactly 20. So if you find one that's rated at 25 or 30, that would be the one you choose, right? So if you looked at it, it said at least what? 20%. So here, the smallest breakover voltage we have, which they call VRRE, repetitive reverse. 4001 is 50 volts. This would do okay if you're operating on 24 volts, right? If I was operating on 120 volts DC, then this guy right here would break over because we're putting it in their reverse bias. So I mean, we would have to go look at this guy, right? That's 4003. If I was operating 440 DC, we would have to go up to the 4005, 4005. So, what they said was the 4001, but that was for that PLC operating at 24 volts. That makes sense? Are we okay? Now, odds are you're not going to see a PLC operating at these voltages anymore. New PLCs try to operate their control, the control under 50 volts. Anybody know why? Why would it be cheaper? It's not cheaper. A lot of people. Safety, yeah. For years we had the National Electrical Code. A lot of people thought that was a safety standard, but it's a wiring safety standard. Okay. This is the way I wire things to keep things from catching on fire, right? You understand? What they realized is there was no safety standard out there that basically covered your safety. So so the National Fire Protection Association, which puts out the National Electrical Code, came out with what they call the 70E standard, which is your safety. So basically it says anything over 50 volts is considered to be lethal. So that means you have to start really putting on some PPE above 50 volts. Below 50 volts, they consider that to be a non-lethal level, and you can get back with, say, what we've got in here. So what's our PPE in here? Safety glasses, right? Normally they say ear protection if you're working in industry, and leather shoes. That's it. That's standard PPE for below 50 volts. So what's happened over the years is just about all your control voltages are dropping down to below what? 50 volts. Now your power voltage, your power is going to be real high. What's the advantage of using high voltage over low? Huh? High voltage over low voltage. Yeah, a lot of people don't understand that. And some of y'all have had my classes before. Is that this is the guy right here. It's power is equal to what? V times I. So I would be equal to what? P over V. So that means different loads are rated at they're rated at a voltage at a certain wattage, right? You understand? So the higher the voltage rating is, then that means I can deliver that power with what? With less current. Now, what advantage does less current have? What's that? What'd you say?
I said it's less dangerous.
No, well, yeah, but you got to understand, I is equal to what? V over R. So your body has a certain amount of resistance. And this is what kills you right here, right? You understand? So when we talk about I here on the left, we're talking about delivering power. We're not trying to make it safe. We're trying to deliver power. The higher the voltage I can make it, the less current is going to be required to deliver that power, but the more dangerous it becomes. Because how much current flow I get to my body is how much resistance I have at the time I come in contact with that thing and how much voltage I get into. Okay, you understand that? So what advantage does a lower current have on delivering power? What advantage does high voltage have in delivering power? We have to deliver that power through what? Through wire. Every wire has a resistance. What determines the amount of resistance? The material it's made out of, the what? The length of the wire, the size of the wire, and the temperature. Alabama Power is trying to deliver gigawatts worth of power. And they're not going to do it on a wire that's as big as this room. They want to try to do it on the smallest possible wire they can do it on, right? They would rather do it on aluminum instead of what? Copper. Why? It's a lot cheaper. Not only is the wire cheaper, but also these big old, not spove. These big old towers are these big that supports the wire. Don't have to support all that weight, right? You understand? So what do? They raise the voltage up extremely high, which means the current goes down. Now we don't have a lot of what electricians call what? Anybody heard of that? Yeah, line loss. So, because every wire's got resistance. If I put current through resistance, I get a what? Get a voltage drop. But what if I raise, so all your high wattage devices on your house, I'm not talking about, all your high wattage devices are designed around 240. Right? You understand? Why? Why don't they, I could do 1800 watts at 120 volts just as good as I could do 1800 watts at 240 volts. Which means I can use, smaller wires. Now I can run them through my wall instead of running them, y'all understand? So high voltage is cheaper to install and cheaper to maintain, right? You understand that? Because we can use smaller gauge wire. Smaller gauge wire means it's going to save me a lot of money. All your low wattage devices run off what? 120. So what advantage does low voltage have over high voltage? That's the only advantage. It's what? Hey, what advantage does high voltage have over low voltage? Yeah, because of less current. Less current, we have less line loss. We can have more resistance in our wire, which means we can either go to another material like aluminum, which is what they do for high power transmission, right? Your big high power transmissions use what? The closer we get to ground, we need to start lowering the voltage down, right? You understand? So we go through these substations. So that's what we can do with transformers. What can we do? You step the voltage up, if you step the voltage up, we're stepping the current down. Everybody understand that? For transmission. So people say, what do transformers do? They say it steps the voltage down, up or down, but every time you got to understand the current's moving in the what? Opposite direction. Now we're not talking about the load. We're talking, if you raise voltage to a load, then current goes up. If you raise voltage to if you lower voltage to a load, the current goes down. We're not talking about the load. We're talking about getting the power to the load, right? You understand? So we're trying to get power to the load. We're not trying to get voltage. We're not trying to get current. So, they'll step up. Just think about it, guys. On these high tension lines, 750,000 volts. They could send 750,000 watts of power with 1 amp of current. But 750,000 volts, I couldn't even get that close to what it's looking for ground, right? You understand that? So we have to put those high tension lines. They call them high tension because they're what? They're high. But the closer I get to ground, what do they have to start doing? They have to start stepping it down till they get to your house. And then when they get to your house, then they step it down to 120 and 240. They're not aluminum. They're usually ceramic. They're not really holding them up. What they found out a long time ago is, first of all, if I used one wire to send the power, if one wire broke, we'd be screwed. And then plus, the size of the wire would be so big, right? I can show you a power supply that sends out the 5 volts might be rated at 50 amps. Instead of doing it on one wire, a big gauge wire, they did what? Send it on multiple different wires, because if this wire is rated at 5 amps and this wire is rated at 5 amps, I use 2 of them, means I can send 10 amps, 5 amps on each wire. So what they do usually on their high tension lines is they divide it into 3 groups. And you ever see them, they run like this. And then they have spacers between them, usually ceramic, because ceramic is a really good insulator. And then if something happens and one of them gets broke, they still got partial power. Plus now the wires are smaller, so they can spool them on spools, right? You understand that? So they usually run them in groups of 3s. Then they'll have 3 groups. Then they have 3 groups because they're sending out 3. So good question. More? You ever watch those guys, those line crew people? They space those things out a real long way. And they'll bring a big helicopter up there. And first of all, people don't understand is that if everything's at the same potential, there's no current flow. So you'll see people working on computers and they say, well, you got to have that connected to ground. No, all you got to do is just be connected to the computer, right? You understand? and then you and the computer is at the wall at the same potential. So these big helicopters, they'll fly up there and they'll reach out there and they'll take a rod from the helicopter and they'll touch the line. And you'll see it arcing because what it's trying to do is get the helicopter at the wall. Same potential. And then those guys that climb out there and they'll climb on those lines, they'll work on those lines, they'll put little seats up there, and why aren't they getting shot? Because there's no different potential. They're on one wire, right? You understand? It's just like birds can land on a power line. Why don't they get electrocuted? They're on the same line. They're on the same potential. What gets them in trouble is when they come trucking across there and get at the transformer, where it comes into the transformer. It's got those two things up there. I've seen several squirrels get that.
Really?
Yeah, they'll be running across the line. They'll jump on the pole. And then they'll have their leg on one side and they're across. If they're on the primary side, they're, 2,300 volts, 2,000 volts, and then they don't feel any pain. Sometimes your lights are blinking. So, guys, we went into a little bit of stuff that probably isn't part of this class, but it's just important stuff just to understand why things are the way they are, right? So everybody okay on MOVs and counter EMF circuits and they call them suppression circuits. But that demonstration where we turned that thing on with the power supply, got almost 80 volts, right? Or it was almost 90 volts. Yeah. And then when I charged that inductor up to 12 volts and took it off and that thing lit up, you can actually see the way those big old inductors, they literally store a charge when you put them on DC. Okay? All right, guys, so what we doing? I know one group's got to go back and, what you need to get in the habit of doing, guys, when you're doing programs like this, is you need to constantly save them, right? You understand? And what's a good idea is to do so many rungs and then save them, and then change the name just a little bit. We got billions of bytes of storage out there where y'all saving these things. So you can save as many versions of it as you want. And in that way, if something happens, you can always do what? Yeah, and I sent in a notice, the TIA portal's got a little problem with the HM program in the HMI panel. When you start playing around with tags, the program will lock up every once in a while. And you don't lose what you had before, you lose all the modifications that you made. So I got in the habit real fast to do what? Save, yeah, at intervals. And the 10-line interval is a really good interval to save that thing. And when you want to save it as a what? Just a name, like add an A or a B or a C or a D or a _1, _2 or something like that. And then when you go back, if something happens, then you know which the last version was, right? Now, odds are when you get through, you'd go back and delete all those things, but that would just a way where you don't lose everything that you got. And you learn that real fast in computers, guys. I'm sorry I didn't bring that up because I've been through that so many times. Before the old version of Microsoft Word, when it first came out, it was, we had these relatively slow machines. And if it did an auto backup, we're talking about, if you had a big file, we're talking about 30, 40 minutes for it to back up. So just about everybody I knew did what? Turn off the auto backup feature. And we had this lady that was working on a application for a grant that basically funds the student support services over there. And she wasn't backing up, and guess what happened? The power fell on the computer. And she lost all the work that she'd done. She was crying on that. So, and I've known that. I should have told you that, but when you're doing that auto or anytime, when you do those small subroutines, every time you get through with one of them, do what? Save it. And then when you get into that auto program, try to save it. It's up to you, 10, 15 runs, or maybe, that, and that way you can always go back. Because we got one group that's got to do what? Start over. Yeah, somehow they got a corrupted file. All right, guys, let's take a break. 5 minutes, right? And then come back and the cabinet's open. Oh, I got to figure out what time we need to start the test. We'll start the test at 11:30. No. No, what time do we get out for lunch? We get out at 12:45. So we're started at 11:45.